Welcome to Demystifying Math. In this lesson, we're going to be discussing force vectors and work. A vector represents both magnitude and direction. The magnitude is a scalar, and that can represent a length, a distance, a weight, a speed, or a force. In this lesson, we're going to be focusing in on the force vectors. If a force is applied to an object, and that force causes the object to move, then work has been done on the object. Suppose we had a 90 Newton force that is applied to move a 15 kilogram object horizontally 20 meters at a constant speed. How much work is done? Well, work is equal to force times distance. In this case, the force was 90 and the distance was 20. The distance is also called the displacement of the object. Our total work done is 1800 Newton meters, or 1800 joules. When an object is dropped, the work is done by gravity. However, when an object is lifted, the work is done by the person lifting the object. Suppose that a 15 kilogram object is lifted 3 meters straight in the air. The force is going to equal the mass times the acceleration. So our mass in this case is 15, and our acceleration is that due to gravity, which is 9.8 meters per second squared. Then we're multiplying those two together, and we get 147 kilogram meters per second squared. And that's a unit of measurement of newtons. So we have 147 newtons. Now to calculate the work, we're going to take our force and multiply by our distance. So we have 147 times 3, or 441 Newton meters, or 441 joules. If the force is applied in an angle, then the amount of work done will be based on the amount of force in the direction of the movement. Okay, so we have this box, and we're going to move it horizontally along this line here, so that would be our displacement. We're going to move it by pulling, let's say, on a string or a rope that's attached here and in this direction, so at this angle to the horizontal. And so the box is going to move this way as we pull on the string at an angle. Now what we want to do is calculate the force that's used, and the force that we need to use is the force that's in the direction of the movement. So we need to calculate this force line, which is parallel to the displacement. Remember that whenever you have a force vector, it has two components, an x component and a y component. So the x component is going to be the magnitude of the force times the cosine of the angle, and the magnitude of the force times the sine of the angle will be the y component. So this length here is the x component of which is force times cosine of the angle, which is going to be in the direction of our movement. Now let's look and see about our calculations. So we have our angle x, which is this angle right in here, about 21.36 degrees. And then we're calculating the cosine of the angle, and then the force times the cosine of the angle, which gives us our 2.1 here. And then you have your work, which is going to be force times the cosine of the angle times your displacement, which is going to be this length here. So we have the work is about 8.4. So let's see what happens as we change our angle. So let's start with our angle being really close to 0, so a very small angle here. And our work is around 9, right? So now we're going to increase our angle. And what you should notice is that as we increase the angle, the work is decreasing. So it's less work to pull at an angle when you want to move an object horizontally than it is to pull directly horizontally to the object. Okay, so we have that. And then, of course, we can always change our force vector. So our force is about 2.3. We can increase our force. And as we increase our force, our work increases. When our force is very small, our work decreases. So remember that's going to involve acceleration as well. And then you have displacement I mean, if you displace it less, of course, don't move it as far, you have less work than when you move it further. So you can see a relationship between the angles, the displacement, and the force. Okay, so let's look at this example. We have a 90 Newton force that is applied at an angle of 30 degrees to the horizontal to drag a 15 kilogram object 20 meters at a constant speed, and we want to figure out how much work is done. So again, we have to use the x component of the force vector because that's going to be the direction of the movement. So we're going to use the force times the cosine of 30 as our force. So we have 90 newtons times cosine of 30, and then we're going to multiply that by the displacement, or in this case our distance of 20 meters. So work is going to be 90 times the cosine of 30, which is square root of 3 over 2, or 0.866, and then our distance, our displacement, which is 20. So you have 1,558.8 joules. Okay, so suppose that we had two forces acting on an object. And what we need to do is find the direction and magnitude of the resultant force, because that's going to give us the direction of the movement. Okay, so a force of 20 newtons acts upon an object at an angle of 45 degrees. So that's our force 1 vector here in red. So this angle coming off the x-axis is 45, and the magnitude is 20. And then we also have our force 2 vector, which is a 95 degree angle from the x-axis and a magnitude of 15. And we want to find the sum of those two vectors because that's going to give us the direction of the movement and the total force that we need to use, because that force will be in the direction of the movement in order to find the work. Okay, so when we're trying to find the sum of two force vectors, we need to first write them each in component form. So for our first force, the magnitude was 20 and the angle was 45. So the components are 20 cosine 45 and 20 sine 45. For the second vector, the magnitude was 15 and the angle was 95. So you have 15 cosine 95 and 15 sine 95. Now we're going to add the two vectors together. So remember that when you're adding your vectors together, you add your x components and then you add your y components. And then in this case, we're just going to estimate those two sums. So I have 12.83 and 29.09. Now to find the direction of the movement, what we're going to do is find the angle of the resultant vector. So I took the arctan of the y component over the x component and got 66.2. So from the positive x-axis to our sum vector, we're going to have 66.2 degrees. Now we also need to find the magnitude of the resultant force. So we can do that by plugging into the distance formula, or you can use the Pythagorean theorem. And I got 31.79 newtons as the total magnitude of the force. So the object's going to move in the direction of the resultant force. And let's suppose that our object moved 30 meters. Then the work done will be the force of the sum vector, which is 31.79, times the total distance moved by the total distance that the object moved, which was 30, and we get 953.7 joules. Let's take a look at some more examples of this. Okay, so I have a force 1 vector here and a force 2 vector here, and the sum of the two force vectors drawn in the middle here. So I also drew this dotted line here, and that's like the addition of the two vectors. So I have my first force vector here that I'm tacking on the second vector to that, and this would be the result of the two forces acting on an object. So what we want to do is kind of look at the relationships here. So what you should notice, I'm going to change my force vectors. As I shrink one of the vectors, hang on one second, there we go. As I shrink one of the vectors, you can see that the resultant vector is going to be closer to the larger force, or the greater force. And this one's just going to have more influence on the sum of the two vectors. as I stretch this one out, you can see that it's pulling the sum vector toward it, so it has more influence now because it's a greater force. So typically what happens is that sum of the two forces is always going to be in between the two vectors that we have there. And the only time that it really doesn't is, let's say that the two forces acted in the same direction. Then you can see that the resultant force is in the same direction, and it has a greater magnitude than the other two forces. And it typically does have a greater magnitude than the other two forces. The only exception is when you have them, the two forces, force 1 and force 2, acting in opposite directions, so they're opposing forces. Then you're going to actually subtract when you add the two vectors together, because one's going to have a negative number in it. And now what you can see is that the sum vector is less than the greater vector there. So you have that as well. So you just kind of get a little relationship between the two vectors and their sum. For our last example, we have a 15 kilogram object that sits on an incline at an angle of 30 degrees. So we have like a ramp here, and this angle at the base here is 30 degrees. And what I've also done is drawn the force vector that represents the force of gravity. And that's going to be perpendicular to the earth, or perpendicular to the base of the ramp. So if this angle is 30 here, then this angle must be 60. And you have this 15 kilogram object that's on the ramp. Now the object's not going to move directly down because the ramp's in the way. What it's going to do is slide down the ramp. And what we want to do is find out how much work is done by gravity when the object slides down the incline. And we're going to ignore friction for this problem. We can easily calculate the force due to gravity, that is the force that is perpendicular to the earth, by doing mass times acceleration. So we have a 15 kilogram object times the 9.8 meters per second squared, which would give us 147 newtons. But this object's not going to move straight down again because the ramp's in the way. So what we need to do is find the force that's parallel to the movement, or parallel to the incline. So in order to do that, we have to take a closer look at our diagram. What I did was I drew another vector that is perpendicular to the incline here. So that's this blue line here. And when I did that, I created a little right triangle here. So if this angle was 60, then this one is vertical to it, so that's also 60. This angle is 90, so that means that this little angle right here is 30. Now when I drew this vector, I also drew one coming over here, and it's perpendicular to the blue line. So this is a 90 degree angle, which means that I created a 90 right triangle. Alright, so we have this angle that's 30. So if we're looking at a right triangle, we can use right triangle trig. So we have the sine of 30 is equal to the opposite over the hypotenuse. So that means that this length, the opposite side, must be the force vector here times the sine of 30. So we have f sine 30 for this length. Now this length needed to be calculated because it is parallel to the direction of the movement. And that's going to be the force that we need to use in order to calculate the work done by this object moving down the incline. Now you could also figure out that this is f cosine theta in the same way, because this is the adjacent side and this is the hypotenuse, so f's cosine 30. So basically we got the components for this force vector. We just don't have our force vector drawn on the coordinate plane, so it's not so easy to see, but you can still use your right triangle trig to figure it out. So the object is moving in the direction of the f sine 30 line. So f sine 30 is going to give us the 15 times the 9.8 times sine 30. So we're taking our force that we figured out on the previous slide, which was 15 times 9.8, and multiplying it by the sine of 30. That's that 147 that we found on the other slide. And then the sine of 30 is 1/2, so we have 73.5 newtons as our force. That's the force that we're going to use when we're figuring out our work. So that's going to be the 73.5 newtons times the distance that the object traveled down the incline, which was 1.5 meters. So we end up with 110.25 joules as the work done by the object sliding down the ramp. Okay, thank you for tuning in to Demystifying Math.